Okay, so in this video we'll get our first sense of what it's actually like to analyze an algorithm, and we'll do that by first of all reviewing a famous sorting algorithm, namely the merge sort algorithm, and then giving a really fairly mathematically precise upper bound on exactly how many operations the merge sort algorithm requires to correctly sort an input array. So I feel like I should begin with a bit of an apology. Here we are in 2012, a very futuristic sounding date, and yet I'm beginning with a really quite ancient algorithm. So for example, merge sort was certainly known to John von Neumann all the way back in 1945. So what justification do I have for beginning a modern class in algorithms with such an old example? Well, there's a bunch of reasons. One I haven't even put down on the slide, which is like a number of the algorithms we'll see, merge sort is an oldie but a goodie. So it's over 60 or maybe even 70 years old, but it's still used all the time in practice. Okay, so this really is one of the methods of choice for sorting. It's the standard sorting algorithm in a number of programming libraries. So that's the first reason. But there's a number of others as well that I want to be explicit about. So first of all, throughout these online courses, we'll see a number of general algorithm design paradigms, ways of solving problems that cut across different application domains. And the first one we're going to focus on is called the divide and conquer algorithm design paradigm. So in divide and conquer, the idea is you take a problem, you break it down into smaller subproblems, which you then solve recursively, and then you somehow combine the results of the smaller subproblems to get a solution to the original problem that you actually cared about. And merge sort is still, to this day, perhaps the most transparent application of the divide and conquer paradigm. It'll just be very clear what the paradigm is, what analysis challenges it presents, and what kind of benefits you might derive. As far as the benefits, so for example, you're probably all familiar with the sorting problem. Probably you know some number of sorting algorithms, perhaps including merge sort itself. And merge sort is better than a lot of the sort of simpler and I would say more obvious sorting algorithms. So for example, three other sorting algorithms that you might well know about, but that I'm not going to discuss here. If you don't know them, I encourage you to look them up in a textbook or look them up on the web. But so three sorting algorithms which are perhaps simpler, first of all, is selection sort. So this is where you do a number of passes through your array, repeatedly identifying the minimum of the elements that you haven't looked at yet. So you do basically a linear number of passes, each time doing a minimum computation. There's insertion sort, which is still useful in certain cases in practice, as we'll discuss. But again, it's generally not as good as merge sort, where you just maintain the invariant that the prefix of the array is a sorted version of those elements. So after 10 loops of insertion sort, you'll have the invariant that whatever the first 10 elements of the array are, they're going to be in sorted order. And then when insertion sort completes, you have an entire sorted array. Finally, some of you may know about bubble sort. This is where you identify adjacent pairs of elements which are out of order, and you do repeated swaps until in the end the array is completely sorted. Again, I just say this to jog your memory. These are simpler sorts than merge sort, but all of them are worse in the sense that they all have performance in general, which scales with n squared when the input array has n elements. So they all have, in some sense, quadratic running time. But if we use this non-trivial divide and conquer approach, or non-obvious approach, we'll get, as we'll see, a much better running time than this quadratic dependence on the input. Okay, so we'll get a win for sorting in divide and conquer, and merge sort is the algorithm that realizes that benefit. So a second reason that I want to start out by talking about the merge sort algorithm is to help you calibrate your preparation. I think the discussion we're about to have will give you a good signal for whether your background's at about the right level of the audience that I'm thinking about for this course. So in particular, when I describe the merge sort algorithm, you'll notice that I'm not going to describe it in a level of detail that you could just translate it line by line into a working program in some programming language. My assumption, again, is that you're a solid enough programmer that you can take the high-level idea of the algorithm, how it works, and you're perfectly capable of turning that into a working program in whatever language you see fit. So hopefully, I don't, it may not be easy, the analysis of merge sort or the discussion of merge sort, but I hope that you find it at least relatively straightforward, because as the course moves on, we're going to be discussing algorithms and analyses which are a bit more complicated than the one we're about to do with merge sort. So in other words, I think this will be a good warm-up for what's to come. Now, another reason I want to discuss merge sort is that our analysis of it will naturally segue into discussion of how we analyze algorithms in this course and in general. So we're going to expose a couple of assumptions in our analysis. We'll focus on worst case behavior. We'll look for guarantees on performance, on running time that hold for every possible input of a given size. And it will also expose our focus on so-called asymptotic analysis, meaning we'll be much more concerned with the rate of growth of an algorithm's performance than on things like lower order terms or on small changes in the constant factors. Finally, We'll do the analysis of merge sort using what's called a recursion tree method. So this is a way of counting up the total number of operations that are executed by an algorithm. And as we'll see a little bit later, this recursion tree method generalizes greatly, and it will allow us to analyze lots of different recursive algorithms, lots of different divide and conquer algorithms, including the integer multiplication algorithm that we discussed in an earlier segment. So those are the reasons to start out with merge sort. So what is the computational problem that merge sort is meant to solve? Well, presumably you all know about the sorting problem, but let me tell you a little bit about it anyways, just so that we're all on the same page. So we're given as input an array of n numbers in arbitrary order. And the goal, of course, is to produce an output array where the numbers are in sorted order, let's say from smallest to largest. Okay, so for example, we could consider the following input array, and then the goal would be to produce the following output array. Now, one quick comment. You'll notice that here in the input array, it had 8 elements and all of them were distinct. It was the different integers between 1 and 8. Now, the sorting problem really isn't any harder if you have duplicates. In fact, it can even be easier. But to keep the discussion as simple as possible, let's just, among friends, go ahead and assume that they're distinct for the purpose of this lecture. And I'll leave it as an exercise, which I encourage you to do, which is to think about how the merge sort algorithm implementation and analysis would be different, if at all, if there were ties. Okay, but we'll go ahead and make the distinctness assumption for simplicity from here on out. Okay, so before I write down any pseudocode for merge sort, let me just show you how the algorithm works using a picture. And I think it'll be pretty clear what the code would be, even just given a single example. So let's go ahead and consider the same unsorted input array that we had on the previous slide. So the merge sort algorithm is a recursive algorithm, and again, that means that it's a program which calls itself, and it calls itself on smaller subproblems of the same form. Okay, so the merge sort is, its purpose in life is to sort the given input array. So it's going to spawn off calls of itself on smaller arrays. And this is going to be a canonical divide and conquer application where we simply take the input array, we split it in half, we solve the left half recursively, we solve the right half recursively, and then we combine the results. So let's look at that in the picture. So the first recursive call gets the first 4 elements, the left half of the array, namely 5, 4, 1, and 8, and of course the other recursive call is going to get the rest of the elements, 7, 2, 6, and 3. You can imagine these as being copied into new arrays before they're given to the recursive calls. Now, by the magic of recursion, or by induction if you like, the recursive calls will do their task. They will correctly sort each of these arrays of 4 elements, and we'll get back sorted versions of them. So from our first recursive call, we receive the output 1, 4, 5, 8, and from the second recursive call, we receive the sorted output 2, 3, 6, 7. So now all that remains to complete merge sort is to take the 2 results of our recursive calls, these 2 sorted elements of length 4, and combine them to produce the final output, namely the sorted array of all 8 of the input numbers. And this is the step which is called the merge. And hopefully you already are thinking about how you might actually implement this merge in a computationally efficient way, but I do owe you some more details, and I will tell you exactly how the merge is done. In effect, you just walk pointers down each of the 2 sorted subarrays, copying over, populating the output array in sorted order. But I will give you some more details in just a slide or 2. So that's merge sort in a picture. Split it in half, solve recursively, and then have some slick merging procedure to combine the 2 results into a sorted output.